Hello, good afternoon, everybody. What I'm going to do now is I'm going to talk about um, density matrices. And our main motivation here to look at these density matrices is to deal with lack of information about the system and the classical randomness that comes with it. Because many times when you're trying to describe experiments or physical systems, the information that you have is incomplete, and you have to find a way of working with this incompleteness. So to understand this better, I'm going to study again the first postulate. I'm going to revisit it. And the question that we are going to ask is if this definition is enough. So if we look at it, we can see that this postulate says that a complete description of a quantum system is given by its state vector. Now, what do we understand by complete description? Because we know that this state vector psi is going to allow us to make the best prediction of the outcome of any existing experiment. So this is what we say, and this is what we understand under complete description. So we need to have a look, and what we can say is that in quantum mechanics, the outcome is intrinsically random. We know that because we write things in terms of probabilities, right? So you have by definition and by construction some intrinsic randomness there. On top of that, the best prediction is going to require you to compute probabilities of measurements and expectation values. So that's also part of it, that you can make a prediction, you can have an outcome, but at the end of the day, we'll still be dealing with probabilities. And we define a state as a mathematical object which is associated with a physical system, which allows us to calculate any expectation value and hence predict the statistics of any measurement of the system. So note here that we are talking about expectation values, and we're talking about measurement, and we're talking also about statistics. So these are concepts that will come up over and over again, and we are going to revisit them because sometimes real life can be more complicated. Because apart from a quantum mechanical measurement containing some intrinsic degree of randomness, there can be other sources of uncertainty or randomness, which are, for instance, associated with imperfections in your experimental devices, which are associated with the correlation between the system you are studying and other systems. So things are not that black and white. And density matrices or density operators, they are more convenient when you have to deal with this kind of situation than state vectors. And we're going to have a look and try to understand why. And the key idea is that you're going to be adding classical uncertainty. So pretty much you are going to include some elements of randomness which are going to arise because you don't have complete information about the system. Quantum mechanically, the randomness is different. Please note that quantum mechanically, you are always going to have some kind of degree of uncertainty. You are always going to have randomness because at the end of the day, you are dealing with probabilities and you're going to perform a measurement on those probabilities. However, on top of that, there may be some information about the system that is lacking. It's not because of this type of randomness, but if you remember, for instance, chaos theory and this kind of theory, you may have some kind of intrinsic non-determinism that you may have some kind of lack of detailed information. You cannot have all the information you require, but your equations of motion, classically speaking, they are still deterministic. So you don't have intrinsic randomness. You just cannot predict things with infinite precision. And on top of that, you also may not have access to many details of what is going on. For instance, if you throw a coin, the probability of getting heads is like 1/2, correct? But this is not quantum. The equations governing the dynamics of this coin tossing, they are classical, but you just don't have access to all this information. Also, if you have imperfect experiments, you have some instruments that are not perfect, they are going to give you the desired outcome with a probability that is smaller than 1. And what do you do with that? Devices are imperfect. You're not going to have in an experiment a device that is 100% perfect. Also, for instance, if you're dealing with a gas in thermal equilibrium, you are going to have properties and probabilities that can be computed from laws of thermodynamics, and maybe this gas is interacting with your system and you don't know how things are going. So these are all possible sources of uncertainty, and this list is just to give you a very tiny example of what could happen, because at the end of the day, this is going to be non-exhaustive. And just to give you an example, let's consider a very simple toy model. And in this toy model, we're going to prepare atoms in a state psi1 with probability p1, and in a state psi2 with probability 1 minus p1, which is p2. Now, this is how it happens because of your apparatus or your devices, I don't know. And we're going to measure an observable wall. And if you consider psi1, the state psi1, the expectation value is going to be the quantum average of O with regard to psi1. And for psi2, the expectation value is going to be the quantum average of O with regard to psi2. But we know that this is not the end of the story, because in the experiment, you're going to have both. You're going to have this, and you're going to have this other one. So hence the question, what more? Hence the question, what is that we're going to have? Because this requires specifying psi1 and psi2, requires knowing this probability, specifying the probabilities, and then you get the result, but it's going to be quite cumbersome. So what people aim at when they're looking at density matrices is to find a single object from which this experimental value of O here can be measured, and which is going to allow you then to reproduce what you have in terms of all the uncertainty that is in your problem, but it's going to be a single object, a single mathematical object. And that's why density operators or density matrices were introduced. And to introduce that, we're going to start from what we know. So we're going to talk about the trace of an operator, and we're going to look at the trace of a matrix. We are more familiar with traces of matrices, right? So what is the trace of a matrix? It's the sum of its diagonal elements, and the same we can say for an operator. If you have an operator written in a matrix representation and you take the trace of the matrix, then you are going to have also trace. So we're going to start from the beginning. And what is very important for us then is to talk about definitions. So we're going to start by defining the trace, and we're going to use this to define our density operator. So let's have a look at the trace. And we know from matrices, we have heard of traces of matrices. So how do we deal with traces of operators? So the trace of an operator A, which is arbitrary, is given by this expression. So you have the sum of AJJ, where these are the diagonal matrix elements of these operators. So here we have then A phi j phi j. So if you see, you have this bra phi j, this cat phi j, and you have this operator here in the middle. And for simplicity, we are saying that phi j form an orthonormal basis, but you're going to see that this is not necessary for the derivations that we are going to do now. And this trace has a lot of properties which are going to be important for us, and we're going to use them in our derivations. So one of them is linearity. Traces are linear, meaning that if you have trace of lambda 1 A1 plus lambda 2 A2, this is going to be lambda 1 trace A1 plus lambda 2 trace A2, whereby these are scalars. Also, if you swap the traces cyclically, or if you have three matrices and you swap these matrices cyclically, you are having the situation where the trace remains invariant. For instance, here we have the trace of a product of matrices A, B, and C. You can bring A to here, which is what is done in the second step, or you could, in addition, bring C to here, which is what is done in this step. And they're going to remain independent or invariant, and they are also independent on the basis that you use. So we're going to prove both cyclic invariance and independence with regard to the basis. And to start now, having a look at cyclic invariance, we are going to consider explicitly the trace of ABC. And we can write this trace as sum over JKL of AJK, BKL, and CLJ, right? Now we can switch this and we can still write this as JKL, BKL, CLJ, and AJK. And finally, this can be, remember that these are numbers, these are matrix elements, so you can swap them around. So this, in fact, if you want to go in more detail, this is trace of BCA, right? What is important here is always that these indices, if you want to do a matrix product, they have to be equal because you normally multiply rows with columns. And here you have CLJ, AJK, BKL, which is going to be here again JKL. So it's going to be trace of CAB. So this is pretty much this property. And with regard to basis independence, what we need to do is we need to consider two bases, two orthonormal bases. So they're going to be phi j and psi j, such that they are connected by a unitary transformation u. So I can say that psi j is equal to u phi j. Meaning then that I can write the trace of A, which is an arbitrary operator with regard to phi, and then I can do a transformation and write it with regard to psi and connect each other. Okay, so let's write then trace with regard to phi of A. This is going to give me J, phi J, A, phi J. Now, if I write this with regard to psi, I'm going to have sum over J, psi J, A, psi J. Note that I'm taking always the sum of this operator over its diagonal elements. That's the definition of a trace. And now what I'm going to do here, I'm going to apply this definition here. So I'm going to write this as U phi j, and the corresponding bra is going to be phi j u dagger. Okay, so this means that this is equal to trace over phi of u dagger a u. I'm not surprised because we have seen also that that's how operators transform, right? And what we need now is to use cyclic invariance. So using cyclic invariance, we can then write that trace of phi u dagger a u. I'm gonna get this guy and I'm gonna move it here. I can do it, right? Trace remains invariant. So this is then equal to trace with regard to phi of a u dagger. But we have seen that these are unitary. So this is an unitary operator, which means that this is, sorry, the identity operator then, because u is unitary, which means that u dagger is u minus 1. And this leads then to conclude that trace of A with regard to psi is equal to trace of A with regard to phi. So if you apply a unitary transformation, if you change the basis, this is going to remain invariant, which is actually quite useful because this means that there is no need to specify the basis as long as you do this consistently. Now, my next step here is going to derive explicitly this density operator because we talked about trace. We looked at the definition of trace and we saw how we work with it dealing with operators. But what we're really interested in is in the density operator, which we're going to derive right now. So let's have a look. And we're going to start from our toy model, where we calculated the expectation value of an arbitrary operator O, assuming that you had, because of your apparatus or the setup in your experiment, you had prepared your system with probability P1 in the state psi1 and with probability P2 in the state psi2. Okay, so this is going to be our starting point. We're going to rewrite this expression that we already had. And we can write this because we're going to use a property of the trace that if you have a scalar, that scalar quantity is equal to its trace. You just have to view it as a 1 times 1 matrix, right? That's what it is. So we can say then that this is equal to trace of P1 psi1 O psi1 plus trace of P2 psi2 O psi2. Now, why do we care and why do we need to do this? It looks like complicating the matter, right? So here we use that every scalar quantity is equal to its trace. So we use this because we want to have a look at cyclic invariance and linearity. So using cyclic invariance and linearity, we're going to have that the trace of P1 psi1 O psi1 plus trace P2 psi2 O psi2 can be written. I mean, we're going to do the following. We're going to swap these. We're going to get this guy and bring it here. This is a cyclic permutation of these three because we're going to have here, if you look back at what we had, it's like as if we had the matrix A, B, C, right? So we can get this guy and bring it here. We have three matrices, one related to the bra, the other related to the operator, the other related to the cat. Okay, so let's do it. And we find then that this gives me trace P1 O psi1 psi1 plus P2 O psi2 psi2. Fine, it's pretty much the same. So fair enough. And this I can also write as trace of O applied to P1 psi1 psi1 plus P2 psi2 psi2. And this here is what we call Ho, which is our density operator. So this means that this expression here is equal to trace of operator O applied to Ho. So we can say that the expectation value of the operator O in our system is given by the trace of the operator O applied to its density matrix, to the density matrix of the system. And we can also generalize. I mean, we considered here only probabilities P1, P2, but in practice, we can take as many as we need to describe our problem. So we can assume that an experiment prepares one of n different pure states, meaning these cats that we are taking, each with probability Pj such that sum from j equal to 1 to n, Pj is going to be equal to 1. This needs to hold because sum of probabilities has to be 1. So we can define then our density matrix as going from j1 to n, sum over Pj psi j psi j. So this is our density operator. And we can also say that the expectation value of an operator is equal to the trace of the operator applied to the density matrix. Note that nowhere in this derivation here, which started here, we assumed that the states were orthonormal. So psi j do not need to be orthonormal up to this point, at least not. It can be in the future. It may be, I mean, you're going to see that if you assume they are orthonormal, this may be advantageous to you, but you don't need to assume this right now. Note as well that whenever there is statistical uncertainty, the density operator is the best description of the state of the system. Note here that we're not necessarily talking about quantum mechanical uncertainty in the sense that we know it, because obviously we know quantum mechanically there are already probabilities that a measurement is going to give a certain outcome. But we are talking about some uncertainty that may come up on top of that, be it because of your experimental apparatus, or because your system is in thermal equilibrium, or because your fonts are imperfect, your sources. So this is going to play a big role. And we have already kind of mentioned you have pure states and mixed states, but we're going to see now this in more detail. So we have here a definition. And if you consider pure states, your density matrix whole is going to consist of a single projector, which is not surprising because you're just going to have ket psi describing the state of the system, whereby if you consider mixed state, Rho cannot be written as a single projector. Here, emphasis on single. We're going to have at least two, maybe more. And this is also a consequence that they cannot be represented by the state of vector formalism alone. So more explicitly, we're going to have this expression for the pure state, and we're going to have a sum over projectors which are weighted by this probability Pj for mixed states. And in the former case, obviously this psi is enough, and here you need to consider several possible states, which are going to be determined by a certain degree of uncertainty that is not necessarily quantum, but that exists. And if you consider that you have an orthonormal basis, you can use the representation that we have seen for operators. We may write Rho is Jk, Rho Jk psi j psi k, whereby this is the matrix element defined as psi j Rho psi k. This is, if you don't remember these check representations of operators as matrices. I'm being a bit lazy here because I'm talking, you have density matrix, but this actually is a density matrix. What we had before is a density operator, which you can represent in many ways. And these operators, which you can write as matrices, if you're in doubt, check our previous lectures, but here we have done this for an orthonormal basis set, has a lot of properties, and they include hermeticity, which means that Rho is equal to Rho dagger. Easy to see. Just come here to the top and calculate Rho dagger. Now you have also linearity. You have unit traces, because the probabilities for measurement of determining outcomes, they have to sum to 1. And also another consequence that you are connecting to probabilities is non-negativity, because non-negative the probabilities have to be non-negative. So Rho is also non-negative. So Rho is going to be bigger or equal to 0. And we know that Pj needs to be equal to 1. Or also we know that trace Rho is equal to 1. And as an example of use for these density matrices and density operators, let's consider, for instance, an imperfect photon source. So we're going to create a photon, and this is going to be created with probability P. So this means that you're going to have P projected onto a state of one photon. So this is one photon state. And you're going to have 1 minus P, that nothing happens, so you keep 0 photons. So another example, our system is in thermal equilibrium, and we're going to consider here a system with non-degenerate eigenstates psi n, meaning also that the eigenenergies are En, and this system is in thermal equilibrium at a temperature T. Now, this is an important piece of information because this means that if the system is in thermal equilibrium, there is a probability Pn. So thermal equilibrium, there is a probability Pn that the system is in psi n, and this probability is going to be given by this Boltzmann distribution. So you have the Boltzmann factor, beta En, and sum over m e minus beta em, whereby I'm using this index here, which is mute to distinguish. So this Boltzmann factor is 1 over kt, where this kb is the Boltzmann constant. And we know then that if we want to construct, and this En is the energy associated with each eigenstate. So let me write this down. This is the energy associated with psi n, and this here is the Boltzmann factor. So clearly, thermal equilibrium the system has to obey the Boltzmann distribution. So if we want to describe the state of the system, we need somehow to take this into consideration, right? And we have a certain probability which is defined by this distribution that your system is going to be in this state psi n. So this means that our density operator can be written as sum over n, and then we include the probability E minus beta En psi n, and don't forget this needs to be normalized. So this is taking into account this kind of uncertainty, or this kind of statistical uncertainty, if you wish, emphasis on statistical, that is defined by the fact, or that is has to be there because the system is in thermal equilibrium at a temperature T. So you have this probability of finding the state in psi n. And we must take this into consideration to be able to describe these things physically. So this was the part of the module related to density operators and density matrices. And next, we're going to see compound systems, which are very useful when you need to bring degrees of freedom together, or when you are dealing with many particles or things like that. This is the next topic.